everybody. My name is Chris Murphy, and I'm an Unreal Engine evangelist. I handle Australia, New Zealand, and Southeast Asia, and my job is kind of supporting developers across the region. So I kind of head between different areas and help wherever I can. Now, for this presentation, we're going to be focusing on high-end effects using Niagara. Now, Niagara is Unreal Engine's new real-time visual effects system that we've been working on for quite a while. It's currently available in early access, and if you want to use it, you actually can do it. Even though it's not officially released, you can go to your plugins menu and literally just type in Niagara, and enable it, okay? Now, for today's session, I want to stress something ahead of time, okay? And this is really, really important. My aim for today is for you to understand what is possible, why the tools are set up in a certain way, and how to start going about it. But I'm not going to be doing a very slow step-by-step, here's what you need to do kind of thing. Because for me, it's much better that you understand what you can achieve from GDC rather than just an intro tutorial that you could probably look up on YouTube at some point, okay? So if I seem like I'm going at 1,000,000 miles an hour, it's a combination of me being both over-caffeinated and me wanting to kind of get to the good stuff, all right? Now, for today's session, we're going to be going ahead and we're going to be creating a Niagara system. And my idea here is we're going to get some particles spawning in a cylinder around this, and eventually they're going to, there's a little drone outside, this guy. So he's flying around, and I want to project a map from him in particles in the world. So this is going to become a sick-looking holographic map. Now, to go about doing that, I'm going to need to do a few things. I'm going to begin by right-clicking and going to FX, and this is honestly, whoa, I didn't do dual pip. So this is one of those areas where people first make their mistakes. When they first load up when they first load up their FX menu in the content browser, they see all of these things when it comes to Niagara, all right? And this is very confusing if you're first coming into it, and believe me, I totally understand why. A lot of people here are coming from a Cascade background where you're used to everything being contained in one little thing. Everything was Cascade. Niagara intentionally separates these out into different things, so it's much easier to extend, much easier to add new stuff, and much easier to share resources between different kinds of systems. Now, the things that we're going to focus on initially are the bottom one, Niagara System, and Niagara Emitter. So essentially, a Niagara system refers to something that is being added into the world and creating particles, okay? Now, a Niagara system contains Niagara emitters. And what I mean by that is, imagine you had an emitter for sparks, okay? And an emitter for smoke, and an emitter for like the boom bit of an explosion. There's a better phrase for that. A Niagara system would hold all three of those emitters to create the explosion, okay? Now, this would be really useful because it means if I go to create another explosion, I can take the smoke that I've already got, I can place it in there as fundamental smoke for what it looks like in my game, and I can tweak those values for this specific effect. But it means I end up with consistency across the board in all of the things that I'm doing. So I'm going to create a new Niagara emitter, and I'm going to base it on a fountain. Now, I'm going to call this circular spawner, because as I said, we want to create something that spawns particles around here. It's worth noting that I don't need to do this as a separate emitter. Like I could use the fountain from the get-go, but for the sake of demonstration, this is just going to be a little bit easier. So this is Niagara as its initial, oh, hang on, there we go. So this is Niagara. You can see here that we've got the viewport. On the right-hand side, we have modules, and down the bottom, we have a timeline. So essentially how this works is over on the right-hand side, you'll see that we have emitter update, particle spawn, particle update. If I scroll up, we also have emitter spawn. Basically, every single one of these blocks is called a module, and that's a series of instructions that is getting run at that point in the system. So the very top, emitter spawn means when the emitter is first created, do this stuff. Then every single time the emitter is updated, tick by tick by tick by tick, those are the instructions that are being run as well. When the particle is first created, these are the per particle instructions that are getting processed. And then every single time every particle is being updated, these are the specific things that are being updated for those. Now, what I want to focus on here is you can see that when the particle is spawned, it's given a velocity, which is that initial burst. And down the bottom, you can see that we have gravity force, drag force, and solve forces and velocity. And this is called a post dependency, because if I get any node here, if I was to look at gravity, this is what the gravity node is doing under the hood. And this is the first thing to note when it comes to Niagara. And that is that every single module that you're adding is something that you can just roll your own Niagara modules and extend as you see fit. But here's the cooler part. So you know how this is calculating force, and it's every one of those modules was calculating force over time and working it out? What this node actually does is it says, look for the variable called physics force. And if that doesn't exist, set it to 0, 0, 0. And this is the first little cool thing, because everything works in namespace. Everything can kind of be arbitrarily created. If I wanted to start adding some modules that just used a variable called heat, there's nothing to stop me from doing that, and then having a bunch of other modules that are looking for the heat value to do something else. I can also feed in that heat value as an instruction for other things again, which I think is pretty exciting. Now, if I look at the gravity force here, it's actually got itself a post dependency. See this required dependencies? This goes ahead and says, I need something that solves forces and velocity. And down the bottom, you can see that we've actually got that, because basically this node says, look, I'm adding force, but eventually I need some sort of node that says, can you do me a favor and add the forces to the object's position itself? You know, work out that velocity change. So having pre-dependencies and post-dependencies is a pretty cool thing. And it's you can make up your own chains to say, look, this is an important part, but it's part of this much bigger system that I expect this kind of emitter to have. Now, after saying all of that, I'm actually going to go ahead and I'm going to strip out everything to do with force and velocity. Okay, and you can see that we're left with just a ball of particles. Now, I want to also get rid of the sphere location, which is currently just spawning them in a very tight sphere. And instead, I want to add a cylinder location to my particle spawn. Now, it's a little hard to see what's going on right now, so I'm just going to crank this number up. You can see here that the particles are spawning inside of a cylinder that we've created, okay? Now, remember that what I want to eventually create is something that is going to fit in the ring around this mesh in the world, okay? Now, to do that, what I need to do is make sure that the measurements that we have here are something that works. Now, I can go up to my viewport, and a nice little trick that you can do that most people are unaware of is if I was to look at the orthographic viewport and hold down the middle mouse as a button, this actually becomes a ruler. And I can see that this is roughly 570 centimeters in radius, okay? A lot of people are just unaware that that's a thing. And that's fair enough, it's a little hidden. So I've gone ahead, I've seen where that is, I see that it's 470, so I'm just gonna read that in as my default value. I could override this later, but I'm just doing it. I'm also gonna go ahead and shrink this cylinder down. Now, I don't want these particles spawning across the tops and bottoms, I only want them spawning around the outsides. So if I enable surface only, this will now only spawn them on the surfaces of the system. And if I disable end caps, we're now left with something that's doing this. Okay, so see how it's spawning all of those particles in a nice ring? I'm going to hit save at this point, and I'm actually going to go ahead and work on it from this point as a Niagara system that I'm going to call holographic map system. Okay? Now, if I was to drop this into the world, I would want to set its position to the same as this. So I'm just going to right-click, copy, go to you, paste. Okay? Now, if I open up the holographic system, we can see that it's working. So the first issue I've got is those particles are pretty big, but that's okay for the time being for what we're doing. Now, what I want to do is eventually project a texture. I want to have these particles all representing a point in a texture, okay? I want them to all take that data. Now, to do that, I want you to imagine that I've got a texture, okay? The coordinate of this point in the texture is 0, 0. And the coordinate at this point in the texture is 1, 1. Okay, so X and Y are from 0 to 1. Everyone's with me? Now, I want every particle to have a value. So what I'm going to do is I'm going to assign every particle on spawn a random value between 0 and 1 on the X-axis and a random value between 0 and 1 on the Y-axis. And to do that, all I need to do is go to particle spawn and say, hey, I want to have a new vector 2D, and it's going to be called particles.uv. And I want that to be set to a random value between 0 and 1. Now, we can't see that doing anything yet because at the moment, this is literally just an arbitrary value that's being stored. Now, one cool thing you can do is if you go to your attribute spreadsheet and hit capture, This actually gives you a listing of every single particle that currently exists and every single value that all of them are storing. And if I was to scroll across, I would see that the UVX and UVY values are actually being held right there, which is fantastic. Now, with that in mind, my next thing to do is to go ahead and just view them in the world, just so I can see what's going on. And a nice way for me to do that is if I wanted to, I could actually go ahead and I could set the position in the spawn directly. So if I was to set the position, I actually can override this with anything I want. But one really nice little thing here is if you use HLSL, if you don't want to roll a full-on node graph to do something very small, or like a dynamic input script for something small, you can always just literally type straight HLSL into this and say, I want this to be a three-dimensional position between particles.uv with 0 on the z-axis, multiplied by 400. And I can then assign all of those values to their position in space. For anyone that's wondering what just happened, what happened was, if they've all got a value between 0 and 1, if I multiply that value against 400, they now all have a value between 0 and 400. And if I set that value between 0 and 400 to be their position in space, we end up mapping them into an isol square. So that's the first thing that I want to do. And the next thing that I'm going to do is I'm going to go ahead and I'm going to go into my particle update and I'm going to sample a texture. Okay? Now, sample texture requires two things. It needs to know the image that's being assigned and it needs to know the UVs of that position in space. So to do this, I'm literally just going to go UV is the variable that we just created. Particles.uv. And the texture is going to be the texture of whatever we want to have there. So if I was to type in demo logo would do. Now we're not going to see a result immediately for two reasons. One is for anything to handle texture data, we need to go ahead and we need to say to it that you are being processed on the GPU. So I'm going to scroll up to the top and I'm going to say you are no longer on the CPU. You are on the GPU, okay? Just select that. Now, the next thing that I need to do is I'm going to scroll down. Sorry, let's keep you running. The next thing I'm going to do is I need to scroll down and I need to actually set this to be the color. This is one of the mistakes that a lot of people have when they're coming from Cascade into Niagara. What they often do is they assume that if they drop a module, it'll just do something related to what it was, because that's how Cascade had to work. Sample texture should just be setting the color, right? No, because we could use that data for all sorts of things, and we don't necessarily want it to override color. Instead, if I open up sample texture, you can see that what it's doing is it's setting the value of sampled color and sampler UV. So it's actually getting that information and storing it inside the module so that anything else can go ahead and interact with that. The reason that's really useful is that if I get this and I look at my system, if I move this above the color setting, there's nothing to stop me on the color from overriding that with the one that we just brought in, right? So if I said access sample color, this will now sample them according to the texture that we're looking at. It's going to bring the R, G, and B in. All right, that's kind of cool, but let's do something better. First off, if I bring in any colored texture as well, you can see that it's going to bring in all of their color data too, right? Okay, that's kind of interesting, but remember that drone that I showed you earlier? So that drone that I showed you earlier, this guy, actually has a render target stuck to the bottom of him. And what that means is that if I look at this, that's an image that's constantly being created by the drone as it flies around. Come on, buddy, stop moving. There we go. So you can see here that that's actually got a drone flying around capturing that render target, okay? So now let's get A and B and like put them together, all right? So let's look at this Niagara system that we've got and say, hey, what if the texture here was actually the camera texture, okay? Now, do you see that there? I'm going to enable real time so it's a little bit easier to see. So it's a little hard to see, but see the yellow dots that are starting to appear? The blue dot here? As the drone's moving, it's actually updating the texture according to the information that we're seeing, okay? Now, this is going to be more visible if I was to go ahead and shrink these particles down, but for the time being, I just want you to understand it, because here's what we've got now. We now have particles representing a texture, okay? And RGB of this texture are the color data, but here's the cool thing. Alpha channel The alpha channel represents the depth. So the alpha channel actually represents the distance that every pixel is away from the camera. Here's why that's cool. If I know the size of if I know the kind of lens we're using, there's nothing that stops me from reprojecting that color back into world space by saying you're at this angle, therefore you're this far away, therefore your particle is at this location. Everyone with me still? So that's really cool, because if I go ahead and do that by going particle update, I want you to now reproject the camera. First thing I want to know is the depth value, okay? Now the depth value is going to be how far away the pixel is. And we know this already because we know that there is a value that is being stored in the linear color. We know that it's in the alpha channel. So I can say, pull the alpha channel from this arbitrary thing that we created, okay? The next thing it wants to know is the FOV, which is default to 45. And it also wants to know the position in UV space, which is, again, simply enough, just the UV data that we created. Now, the final thing that it wants to know, and you can see it's starting to take effect in the distance there, is which direction to project it in. It doesn't know which way the camera is facing. So all I need to do is tell it to project downwards, okay? And to project downwards, I literally said this to -1, 1, oops. Oh, and I forgot to zero this out. Now, it might be a little tricky to see, so I'm just going to crank up the size for the time being. I'm going to turn this up to, say, 20. Now, see down the bottom there? What we're starting to see... Yeah, I'm going to make you way bigger. Oh. There we go. What we're actually seeing down here is the world is getting recreated in particles that are equal to their position in space, okay? Now, that's a really kind of a weird way to show it, but we're going to make it cooler in a second. I just want to start here. So the next thing that I need to do is this. I've got particles that are way down below where my emitter is. Now, the reason for that is this, is when I reproject the camera, what I'm actually doing is I'm putting the particles all the way down to how far away the surface was from the camera itself. So I need to move it upwards. So I need to offset that position by a certain value. Once I've got it around the emitter, I need to scale it inwards by the size of the lens, and then scale it outwards to the actual size that I want it to be, okay? Now, I could do this in a number of different ways. If I wanted, I could just be crafty with HLSL, but let's say I wanted to use a node graph. All I would need to do is right-click, go to FX, and create a new Niagara module that was called Adjust Camera Projection, okay? And this is where I can just start to roll my own additional solutions to this stuff. First thing I need to know is some sort of vector that's storing the position of the particle. The next thing I need to know is another vector that stores the offset direction. The next thing I need to know is the distance away that currently is, which is going to be called offset distance. Finally, I'm going to need to know the angle of the lens and the size that we want this to end up as. Okay? Now again, this is the most boring section of this presentation, but just give me a second and we'll get there. So, we've got all of these things. Now, if I want to offset its position, all I need to do is multiply the direction that we want it offset in against the distance. Okay? And I'm going to put in some default values here just so that they are seated by default, and the direction is going to be, it's currently offset downwards. Okay, now if I was to plug this in, there's nothing that would stop me from just getting this, putting it into there, and putting it into there. Okay, so if I did this and just quickly applied it, I'm just going to add this to the particle update at the end, okay? I'm going to add set position. Oh, no, I want to add camera projection. So adjust camera projection. And if I move this, we're now going to see that this has moved up, but it currently doesn't know the camera's position. And the reason for that is I need to set the default values for here as 45 And the current position is just going to be bound to the variable that we have from that camera projection. And when we do that, we can now see that it's creating it around the origin of the system. And because of that, I can actually shrink these down to be a little bit more visible. And if I wanted to, I could crank up this spawn rate as well to get something pretty cool. Gonna hit save. Now, if I look at that in the world, let's go back to this emitter and I hit play. Oh. One moment. Have I missed a variable? Sorry, 1 second. 45, offset direction, -1, 7,000 scale is irrelevant right now. Position is camera projection. Okay, I'll work this out in just a moment. I'm going to move you outwards so we can see you. Okay, that is working. The particles are just too small to see. Good job, Chris. You scaled them down too much. So I'm going to set these 5 for the minute just so we can see them. There we go, maybe 20. Okay, we're getting something a little more interesting, but see how I can actually see the environment? And as I run that drone so that it's driving around, I can see the actual system changing to compensate for the surfaces of that environment. Next thing I need to do is scale it down into itself and then scale it out again. And that's actually as simple as getting this position and saying to it, I want to transform this position into local space so that you crush in on yourself. So I'm going to get that and I'm going to transform position. And I'm going to say you go from world to local. Okay? I'm then going to divide this by a size, because if it's 5,000 units across and I divide it by 5,000, it's now a value between 0 and 1. So I'm going to divide you by a size, and the size I'm dividing it by is actually rather simple. At the moment, the distance is the ground to the lens, okay? Which means that the distance from here to outwards from the lens angle is equal to the tangent of this angle multiplied by the distance, all right? I know I'm busting out the high school math, but let's just roll with it. So I'm going to get the tangent of this. Tangent in degrees. Multiplied by this distance is what we're dividing it by. And then we're multiplying it by the scale of this to make it as big as this scale. Because if we bring it down to a value that's between 0 and 1, and then I multiply it to a value that's, say, between... if I multiply by a value of 600, it's now going to be a value between 0 and 600. Okay? So just punching that in. Excellent. And now we need to do one last thing, which is convert it back from local space into world space. Plug you in. And in theory, all right, give me just a sec. I'm going to load this up. I'm going to scroll down. Now the scale is currently not default. There we go. So I'm going to delete this and just look at the one inside. This is now what we're looking at. It's super bright. Give me a second. Let's go ahead and fix that up. Okay? Now, there we go. So we can now see that we're actually starting to create a pretty interesting interior holographic map. You're not allowed to grin yet. We can make this look way cooler, guys. Come on, bear with me. So we've got this spawning as particles that are just doing their thing, all right? And that's kind of interesting. But remember the first thing we did when we created that cylindrical spawner? What about we go ahead and do that? What about if I go here and I say, be gone with you, HLSL, that we created. Instead, I want this cylindrical location. And instead of saving this off to particles.position, what if I turned this into something called particles.projected position, okay? Now, if it's a projected position, this means it's just automatically gone off and created a new variable to store that we can access. Now, the reason I might want to do that is actually rather simple. If we store the projected position instead, and I disable the intrinsic calculation over here, we can see that the particles are now spawning as a cylinder, right? But see how some of them have little red dots and blue dots in them? That's because they know where they're going to go. I've just set their position differently, okay? Now, here's the fun part. If I go to my update loop and I say, I want to set the position of the particle, but I want to set it so that over time, it smoothly, oops, sorry, wrong one, there we go. It smoothly lerps over time from itself to its target value, which is the value that we just made up. What we're left with is this. Now, that might be a little bit weird, but what these are doing is those particles are trying to make a map, but they're not fast enough to do it. They're dying before they get there. But I could just crank up my convergence rate, and now the particles are whisking away from where they start into their final position, all right? But we can do cooler than this, because why don't we get this convergence rate and change it over time? Why don't we say convergence rate U are set to a curve, and when you're first initialized, I want you to actually have a value, convergence rate of near 0, all right? That means that as the particles create, see they're now chilling out for just a second before whisking away? That's because when they first start, they're not allowed to converge, and then they are. And what we end up doing is creating something that over time, if I add this and I can change their convergence rate as I see fit, and I can scale the convergence rate max and mins, say to 10, here's the fun thing. Those particles are now going to dynamically move up and down. So when the texture moves, they go, whoop, I better move downwards. Whoop, I better move upwards. So you get that really cool like flow between the particles as they move up and down. And the other fun part here is that if I was to throw it into slow-mo, if I was to throw this into slow-mo, you can physically see each and every particle, let's follow this yellow guy, over to exactly where it needs to be in the map. And then, of course, depending on how much you want to tweak this over time, you know, we can do that without too much drama. I can change this, for instance, you know the color value that we set before? Nothing stops me from getting this color value and saying, hey, you know what? When you start, you're actually going to be green. And then I slowly want you to convert from green into the actual color that you're becoming. You know, or if I wanted, I could create a jewel ring effect by saying, hey, this curve that we created, what if we stop converging you at some point? So we do like a real close secondary ring, and then you crank up again. So if I got this, we kind of did a little bit of a hop before eventually getting up there. Those particles are now going to whisk out, slow down, and then whisk out again. I'm just going to bring that in a little closer and bring you a little lower. So we should create a secondary ring in the process. And again, this whole thing is acting live based on a camera from this guy out here. Now, here's what I'm going to leave you with as we're kind of running out of time. What I'm going to leave you with is this. Look, Niagara is a pretty cool system, and obviously you can do some stuff that you couldn't do in Cascade. But I really want you to consider what that actually means. Okay, I'm going to turn up the particle count so we have something cooler. What that actually means is this. I'm not excited for the explosions that you'll make in Niagara. I'm not even excited for the beams or anything else, because you could make them in Cascade and you could do pretty well. What I'm excited about is this. In any other particle system that we've ever had, or any other engines really had on this front, typically when an artist hit a roadblock on what they were trying to create, they would either have to get a programmer or give up and do something different. And what I love about this is anytime you want to reach under the hood and change it and warp it and add to your, extend it to whatever you want it to do and add any subsystems that you want them to have, you can do it now. It's not actually a limitation. And what I'm excited about is all of the stuff that people are going to do that we've just never seen in games before. Because this took 25 minutes while explaining what I was doing, And normally this would be an effect that you would fake with a 3D mesh and some transparency, and you'd be like, I guess that's good enough. But when you actually have these things, there's nothing to stop me from spawning these particles from a character's skin and literally turning the skin into a map and then back into a character again. That's actually only a couple of nodes. So I'm super excited about where people take this all, and I hope you enjoy the rest of GDC. Thank you very much for coming to this presentation. Stick around, we've got Learning Theater stuff all day.